Okay, yeah, thank you very much. So I think the summer school's been going since 2013, I think. And I think I've been to every one, embarrassingly, apart from the few that are overseas. And the last few years, it's been my pleasure to give the first introduction to Gaussian processes to GPs. And one of the nice things I like about the summer school is that we always have two introductions. So I'm in the first one, Carl Henrik's given the second one, and we've not really talked to each other about what we're going to do at all. The whole idea is you'll hear the same things twice, or some of the things. You'll also hear completely different things. And it just gives everyone a chance to, digest the key material more slowly. Okay. So I've got way too many slides. I've never once got through them all, and every year I add a few more. Okay. And that's absolutely fine. The ones at the start are the ones that matter. The others are kind of extras that are more advanced techniques that you might see later in the week. And I think what's really important is that this becomes a conversation. If there's questions or anything's unclear, just ask me. Okay? Stop and ask, and we'll clarify things as we go. Okay? We'll get through all the key important information, what the definitions are, and what a Gaussian process is, and then we'll see how we get on from there. So just to talk briefly about some application areas that GPs are used in. So these are all kind of my area. They're not all my work, but they're all my kind of area. So the research workshop on Thursday is on digital twins. So digital twins is jargon that's become popular, but it's often thought of as where you've got data and models, and you want to combine these to model a real-life asset. Okay? So, for example, at the bottom here, I've stolen that picture from Pratt & Whitney. So they decided to try and incorporate uncertainty in all of their airplane designs, okay, about a decade ago. And the key part of how to do that was having these complex models of airplanes, the different parts in their airplane. And the models were too expensive to run by themselves over and over, the same amount of time you need to run them in order to do statistics. And so they used Gaussian process methodology to create their digital twin of airplane engines. Okay, so like that. The top plot is from my work. That is two sides of a patient's left atrium. Okay, so the atrium is one of the four chambers in your heart. And what we're interested in is building digital twins of patients suffering from various heart conditions. So in this case, suffering from atrial fibrillation, when the heart doesn't beat regularly. Okay, it has a weird rhythm. And so we collect data on the surface of the heart, on the surface of the atrium. And then we want to interpolate it, fit complex models to it, and so on. And the key tools that allow us to do this are Gaussian processes. Okay. Another application here with Maurizio. This guy in the middle of the motorbike is a Boda driver in Kampala, okay, Uganda. And he's got an air pollution sensor attached to the front of his bike. And we've got a network of air pollution sensors deployed around the city of Kampala, each measuring the air pollution. And what we want to be able to do is to interpolate the air pollution, say what it is everywhere, say what it will be tomorrow, and say what's causing it. Okay? Now, the kind of models that you use to do this are again, too expensive, too complex, and we have lots of unknown things going on. And so we're modeling the unknowns here with a Gaussian process and then fitting it in this kind of complex regime. Okay. And there's more, and you'll see lots this week. But my point is that GPs are used widely nowadays across statistics, science, machine learning, you name it, as tools for modeling unknown functions in a variety of ways. Okay, so what we're going to do this talk then is going to start by talking about Gaussian distributions, which you've probably all seen at school, if not at school, when you started A-level. Okay? And we'll talk about multivariate distributions to begin with, just to get the ideas fixed. And then we'll move on to Gaussian processes. Okay, and I'll explain what the difference is between the distribution and the process. And then we'll just see pictures for a bit about what different Gaussian processes look like. And then I'll talk about a number of different motivations for why we use Gaussian processes until we run out of time, basically. But as I say, any questions at all, please stop me, interrupt me, and ask. Okay, so you've all seen this before, but just to get the idea in the head. This is a univariate, so a one-dimensional Gaussian distribution. Okay, so you've probably seen things like this before. So if y is our random variable, we write Twiddle's normal with some mean, mu, just an integer, a real number, and a variance sigma squared, or positive, or non-negative real number. Okay? And on the left, I've plotted its probability density function, its PDF. Okay, that's this famous bell-shaped curve. And on the right is its CDF, its cumulative distribution function. Okay, so I'm sure you've all seen these before. So the thing on the right is not known, but we've got tables we can look at it up in. It's computable to high accuracy. Okay. Okay, so why are these so popular? Why do Gaussians appear everywhere? Okay. And one of the big reasons why Gaussian distributions are used everywhere is that they're mathematically convenient. That convenience translates over to Gaussian processes quite often. So first of all, it's a closed family under lots of different mathematical operations. So we can add Gaussians, and they're still Gaussian. We can multiply them by stuff, they're still Gaussian. We can add things to them, they're still Gaussian. And when we get to Gaussian processes, we're going to find even more kind of operations we can do. We can differentiate them, we can integrate them, and so on. Okay? We can translate them, and they'll remain Gaussian processes. We know there's a central limit theorem, so if you add up lots of random variables, IID random variables say, that sum, or the mean of the sum, converges to a Gaussian distribution. So they appear naturally in our theory, okay, where we have a lot of things start to look Gaussian. But they have a number of other niche properties which you might be less aware of. So one is this maximum entropy or maximum surprisal property. So if you think of all distributions that have mean mu and thick variance sigma squared, okay, so nothing else about them, and you think about which of those distributions is most surprising in the sense of maximizing the entropy, so entropy is a measure of surprise, the Gaussian is the most surprising. Okay? So there's a whole field of statistics based on this principle, this maximum entropy principle, that says if you don't know a distribution, you should use the most surprising distribution you can, the maximum entropy distribution. And so in lots of cases, if you just know the mean and variance, you'd pick a Gaussian variable to model it by. They're infinitely divisible and other properties that mathematicians like. If you've got two of them, two random variables that are jointly normally distributed, and they're uncorrelated, then they're independent. Okay, so you've probably seen that before. It's pretty much the only family for which that's true. Okay. And perhaps the final motivation is that many of the algorithms we write down have an interpretation, a probabilistic interpretation, in terms of Gaussian errors. So, for example, suppose we're fitting some model, f of x, that's parameterized by beta to some data y. Yeah? So you want to predict y with that model f of x. And one way we might do that is to choose the betas to minimize a sum of squared errors. Yeah, like least squares regression. You look at the errors, you square them, you add them all up. Okay? Well, it's easy to see that this is equivalent to maximum likelihood estimation, assuming everything's Gaussian. You've got Gaussian errors. Okay? So lots of these algorithms that scientists wrote down, or statisticians wrote down, using squared loss, because squared loss is nice and differentiable, turn out to be probabilistic models of Gaussian errors. So these Gaussians appear everywhere. Okay. So that's one random variable. Let's think about what happens if we have two random variables. I just want to be really slow, and then we'll transition from here to two to many to infinite number of random variables, and that will give us a process, a Gaussian process, when we go from two to many to infinite number. So let's suppose now we've got a random variable y that has d elements. Okay, we'll start with 2, I guess. Okay. So we say it has a multivariate Gaussian distribution, and we can specify that Gaussian distribution fully by its mean vector, so that's a vector of the same size, a vector of length d, okay, and a covariance matrix. I'll write these things down in a minute. Okay. So that's going to be a d by d matrix. And we're going to write the same thing as we had before. I'll just put a subscript here to denote that we've got d of these things now. So for a bivariate Gaussian, we'll see some pictures in a second. We've got two numbers, y1 and y2. We've got a mean for each of them. And we've also got the covariance matrix here. Okay. The diagonal elements here, so sigma 1 squared is the variance of y1. Sigma 2 squared is the variance of y2. Okay. And the cross terms here, which are the same, they're the covariance between y1 and y2. Okay. So I assume you've all seen this kind of thing before, have you? Yeah. Okay. So just some pictures, and we'll generalize from here. Okay. So here is a selection of points in 2 dimensions. So there's a point on the x-axis, a point on the y-axis, okay? And these points have got mean 0 and covariance matrix, that's the identity. And there's various things we can see here. Well, first of all, the correlation between y and y1 and y2, the off-diagonal terms here are 0. So here we know that y1 and y2 are independent, just completely different random variables. We also have the marginal distribution, so that means if we just looked at all the y1 values here and plotted a histogram of them, they look like normal random variables with mean 0, variance 1. Okay, we can just read off the marginals. The same for y2. If we just observe y2, it would just look like a univariate Gaussian cloud. And because they're independent, there's no additional knowledge to be gained here. So if you came along and told me y2, it wouldn't tell me anything more about y1. The distribution of y1 given y2 is still normal 0, 1. Nothing's changed. It's the same as marginal. Yep. This is a really boring multivariate process in that it's just independent things stuck together. Okay. So we can change things here. So I've changed the mean here. So the mean changed to be 0 on the x-axis for y1 and to 1 for the y-axis. So it's just shifted the cloud up a bit. And I've made the variance smaller here. So it's 0.2 for y2. Okay, so it's just changed the shape of this cloud. But they're still independent. We've still got zeros here in the off-diagonals. So it's still kind of uninteresting. Okay. So let's start to get a little bit more interesting. So here, I've gone back to the 0 mean, but now I've allowed them to be correlated. Okay, so they've got a correlation of 0.9, and you can see there's a strong kind of linear relationship between them. There's a strong correlation here. If you were to tell me y1 here, yeah, if you were to tell me y1 was -3, so right down here, that's a point here. Okay. If you were to tell me it was -3, I would know quite a lot about y2. So there's information about one variable from the other variable. The marginal distributions haven't changed here. So if you plotted these histograms 1 dimension at a time, nothing has changed at all. They still look normal 0, 1. Yeah? It's only when we plot them together it looks interesting. But just to kind of preempt what we're going to do later, a question is, what would be the conditional distribution here of y1 if someone came along and told you, like I said, that y2 equals 1? So suppose we knew that y2 took the value 1, that's this line here. Well, what could we do? We could go across this line and kind of read down to where all the points were. Yeah? So yeah, I know you can't see the numbers on it here, but you get a good idea that y1 had to be in this kind of range here if you were told that y2 took this value up here. Yeah? So there's clear information that we can read off these charts. And in fact, we'll see the formula for doing this later. In fact, the answer is here that the distribution of y1, given that y2 is 1, is, well, we expect it to have value about 0.9, and we expect its variance to be about 0.2. Okay, we're going to see that formula for how we do that. So that's changed from here, where the marginal was 0, 1, normal 0, 1, to being normal 0.9, 0.2. Okay. That's our extra information here. Okay, we can keep doing things here, so I've just scaled the variance and so on. Okay. You can make them really highly correlated, so you can make the correlation 0.99 if you like. And as that correlation there approaches 1, you get a straight line. They'll all lie perfectly in a line, be perfectly correlated. Okay. So what we're going to do now is go from 2 dimensions to 5 dimensions to infinite dimensions. Okay. But to help visualize it, I'm going to draw the plot slightly differently. So in this last plot, I had my y1 variable on this x-axis, my y2 variable on my y-axis. But with 5 variables, I can't do that anymore. Okay. So what I'm going to do is, instead of plotting like on the left here, like a scatter plot, I'm going to have an index along the bottom, okay, and I'm going to join the points. So if we just pick out one of these points, so this point up here, okay, it's got a y1 value of about 1.6 or something, and a y2 value of about 1.6, and that becomes over here for index 1, I plotted it here, it's 1.6, and index 2 is 1.6. Yeah. This blue point, similarly, is this blue point over here. So I've just taken the same information and plotted it slightly differently. Okay, does that make sense? What this allows us to do then is to have more than 2 variables. So here I've got 5 variables. Yep. So each line here is 1 point in 5-dimensional space. It's got 5 values attached to it. The first value is for index 1, second value is for index 2, and so on. Yep. And I've joined them up so you can tell what points belong together. So each line you can think of as 1 point, or 1 sample from my 5-dimensional space. And so we're going to start to think about these things as lines. And we can keep going here. We can think about having 50 points. Yep, so I've got a 50-dimensional multivariate Gaussian distribution now. Okay. So I've got 50 indices along the bottom. And I've got this correlation matrix so that the points are highly closely related to each other when they've got similar indexes. Okay, so point 1 and point 2 are very closely related. Okay? And the further you get away from each other in terms of the index, the less closely related they are. Okay. Again, each line here is 1 sample in 50-dimensional space. So this is how we think about Gaussian processes. Okay? This, but instead of having an index set of 50 points, so here I've got 50 variables, so I could have variable 1, variable 2, up to variable 50. I'm going to make that index set a continuous set and have an infinite number of random variables. Okay? And take this to the limit, essentially, where it becomes a line. Okay. So, just quickly then, a definition of these things. So, for those of you who've studied maths to a high level, you'll have seen all this before, but what is a stochastic process? A stochastic process is just a collection of random variables indexed by some variable. Okay? So y here is my stochastic process. Okay? And I've got an index variable, x. Yeah? So on this previous slide, my index was 1, 2, 3, 4, up to 50. Okay? I've just generalized it, so now I've got an index, x. This could be a collection of numbers, it could be names. Yeah, so you're one big Gaussian process here, so we've got Bob and Jill and so on. That's my index set, okay, your names. But here, x could be anything. This is a stochastic process. Now usually, and for today, our random variables are going to be real numbers, so y is a real number, and my index set is normally some subset of Euclidean space. Yeah? So like an interval, something like that. So this looks like a function. Yeah, this is how we kind of define functions as well. So you can think of this as a function. This is a random function that we don't know. It's a function of x. Okay. This is our random process. Okay. And if the number of indices we're considering here, if the size of x is infinite, then y is an infinite dimensional process. Yeah, there's an infinite number of terms in my stochastic process. So for example, if I let my index set be the interval 0 to 1, all the real numbers between 0 and 1, there's an infinite number of them. So I've got an infinite number of random variables. Each index has a random variable associated to it. And so I've got an infinite number of those things. So this sounds very complicated, but thankfully Kolmogorov showed a long time ago that all we need to know in order to understand stochastic processes are what are called these finite dimensional distributions. So in other words, if you pick any finite number of the random variables, so let's pick n indices, x1 up to xn, then we consider the variables at those indices, so that's y at x1, y at x2, y up to xn, then all we need to be able to do is say what the distribution is of those n random variables. And if we can do that for any finite collection, if we can say what that is, we know everything there is to know about the stochastic process. Okay. So this is the last technical point, okay, then we'll get on to pictures. Okay. So a Gaussian process is a stochastic process where all the finite dimensional distributions are Gaussian. So in other words, if I pick any finite subset of my stochastic process, any finite set of points, they have a multivariate Gaussian distribution. If that's the case, then Y is a Gaussian process. Okay? So this is all a Gaussian process is. It's an infinite number of variables, okay, whereby if we look at any finite subset of them, they have a Gaussian distribution. Yeah. And because they have a Gaussian distribution, all we need to be able to do is say what their mean is and what their variance is. Their covariance is. Yep. So that's all we've got to be able to do here. Okay. And what we normally do is then denote, we write something like y dot, okay, to indicate this is a function of some index, twiddles GP to denote it's a Gaussian process. Yeah? And this is kind of shorthand for saying we're going to model the unknown stochastic process Y as a Gaussian process. And the best way to think about this, which we'll see in the pictures, is to think of this in terms of functions. Okay, any questions at this point? I know that's quite a mathematical way to start. Lots of pictures coming. Okay, so just interrupt if there are. So remember, when we had a Gaussian distribution, okay, multivariate Gaussian distribution, we said that to specify how it behaves, we just need to specify its mean vector and its covariance matrix. Okay. It's the same for Gaussian processes, but now instead of a mean vector, because we might have an infinite number of terms, we have a mean function. And instead of a covariance matrix, we have a covariance function. Okay? So if we often write things like this, we say that Y is a Gaussian process with mean function M and covariance function K. Okay? And given any finite section of inputs, the mean function and the covariance function will allow us to write down the mean vector and the covariance matrix for those finite collection of points. Okay, and we'll see that lots of times. Okay. Yep, so M of x is the expected value of Y at x, and K of x prime is the covariance between Y of x and Y of x prime. That's our covariance function. And if we can specify M and K, yeah, once we've specified M and K, we know everything there is to know about the Gaussian process, or we can know it. Yep. That tells us the whole process, once we know M and K. So that's our goal in modelling, is to pick a good M and a good K. Now, as we'll see, M doesn't matter so much. I mean, it does in applications, but what really determines the flavour of Gaussian processes, the character, is the covariance function here, K. Okay, so we'll see some pictures with different choices for K here. So there are rules about what we can do to pick these things. So as I say, the main function, we try to pick them in various ways. The most common way, kind of trial and error, essentially. We use the knowledge we have of our problem, okay, and think about what might be a good mean function, a good covariance function, subject to some rules, which I'll now tell you. Okay. And then we do it by trial and error to try and optimize that choice. We can be clever about it, try and optimally pick the choice somehow, but often it's just trial and error. So the mean function is easy. We can pick whatever mean function we want. Yeah? No rules at all about the mean function. Yeah? It doesn't have to be continuous, differentiable, anything like that. Okay? You can be as imaginative as you like. Overwhelmingly, the most common choice is to pick 0 everywhere. Okay? Often, people might make it a constant, okay? But often they'll just remove that constant from the data and just assume it's 0. In statistics, we often like to have parametric mean functions, but it's less common in machine learning, where they have lots of data, so they'll try and learn some of the ways. Covariance functions are where the headaches start, okay? So covariance functions are what's going to cause us all the problems you have with Gaussian processes. And there are problems when you use Gaussian processes, the numerical errors and so on. Okay? So our choice for the covariance function is we normally pick something that is a function of the indices only. We don't have to. Okay? That's our normal choice here. We normally set the covariance between y of x and y of x prime to be some function of x and x prime. Okay? We'll see pictures in a second. And our key restriction here is that K must be what's called positive semi-definite, okay, which I won't bore you with the definition, but it basically says when you work out what the variance matrix is, it's got to be a variance matrix. Yeah? You can't have negative variances, is basically what it comes down to. So there's some technical conditions that we have to satisfy, and they can be tricky to verify. Okay? So in practice, what we tend to do is pick from a small set of covariance functions that we know are valid. Yep. So there's a set of 5 or so families of covariance functions, and we tend to always pick one of those. I mean, you could do much more advanced things than that, but that's the default starting point, is to pick one of our kind of favourite ones, because we know we're not going to get in trouble. We often simplify these things, so we often assume stationary processes. So what's a stationary process? Or a stationary process says is that if the covariance between y of x and y of x prime is just a function of the distance between x and x prime. That means when we translate our process along the x-axis, it looks the same everywhere. It doesn't matter if we're considering the covariance between point at 0 and at 1, or between 100 and 101. It looks the same. It's stationary. So people might talk about stationary covariance functions, and they're pretty much all you'll see this week for most of the talks. Okay, stationary covariance functions, where you can write them like this. Okay, we also have things that are isotropic. So if x is more than one-dimensional here, okay, we often have a norm over it. So that says it's the same in all directions. So it doesn't matter whether you're facing north or east when you take the distance. Okay, it's the same kind of distance that matters. Just the metric distance. So if it's Euclidean, it's the crow fly distance. That's all that matters. And I'll say it again. K really determines the nature of the Gaussian processes. Okay? So K determines the space of functions we're considering here. And so it's K that we really focus on, this covariance function. Okay. Pictures. Now, pictures. So one of the most commonly used covariance functions sorry, excuse me, is this covariance function here. It's got many different names. Okay, so people call it the RBF kernel sometimes, for radial basis function kernel, or the squared exponential, or probably its preferred name, the most accurate name, is exponentiated quadratic. In that you've got a quadratic in x, the distance between x and x prime. Okay, distance between x and x prime squared, exponentiated. Yep. And what I've drawn here, I've got my index set is all the real numbers between 0 and 5. Yep, so that's my index set. So I've got an infinite, for any value of x between 0 and 5, my random variable's got a value. My stochastic process has got a value. Okay. And I've drawn on 20 samples here, I think. Yep. So each sample is one line, one function, essentially. Yep. So if we take this black one at the bottom, it's continuous. Yep. It's differentiable, it's smoothly varying. Yep. So we can see that if you take two input locations that are close together, okay, so if I consider my value of my random variable at 1, say, and at 1.1, so close to each other, the functions are close together. Yep. So within one colour curve, there's not much variation. But if I look at, so the correlation between my function at 1 and at 1.1 would be very high, 0.99 or something like this, or higher. Okay? But if I look at the correlation between the function value at 0 and the function value at 5, there might be very little relationship. Yeah? It can vary quite a lot in that distance. Okay? So the closer we are together, the closer x is to x prime here, the larger this covariance is, the closer it's going to be to 1. So this covariance function, although commonly used, is a little bit dangerous. We'll talk about why a bit later, but this produces very smooth curves. In fact, these curves, these functions it produces are all infinitely differentiable. They're analytic. They've got derivatives of all order. Okay? That makes them very slow to turn round, essentially. Once you're going up, it takes a lot to change the direction. We can change things in this covariance function, so we often parameterize these covariance functions. So one thing we might do is divide the distance by a number. We call this number the length scale. Okay? So what that does, if I divide by something small, that makes this number bigger, so it makes it vary faster. Okay? So if we think about here, I'm dividing by 1. So this I'd say has a length scale of 1. Here, I'd say it's got a length scale of 1/4, 0.25. And this length scale tells me how quickly the function might change. So these are still smooth, still continuous, still infinitely differentiable, but the variance drops off a lot faster. So here, they've got a characteristic length scale of about 1, so it means that you have to go a step of 1 to see much change. Whereas here, length scale of 1/4, you have to go a step of about 1/4 on the x-axis to see a change, much change. Okay, so that's our length scale. If we make the length scale bigger, so length scale of 4, they hardly change at all over my input set. Yep, there's very little change with a step of 4. Okay. We can also put numbers at the front. Okay, so we multiply a number at the front, and all that does is change this y-axis here. You probably didn't notice, but before they were varying between 3 and -3. All that's changed here is I've multiplied by 100, I've changed the standard deviation by a factor of 10, and so they vary now between 30 and -30. Okay? So it's just changed the variance. So there's two numbers to play around with in these things. A length scale and a variance at the front. Okay? And these are numbers we'll have to estimate from data somehow. Okay, so that was all RBF kernels, or exponentiated quadratic kernels. What other kernels are there? Well, there's a family of kernels called the Matern family. And the Matern family, there's a whole load of them, okay, of different degrees. So here I've picked out 3/2. Okay? You tend to only see a few of these. You tend to see Matern 1/2, 3/2, and 5/2. Okay? So that's the form of the Matern. And the difference you'll notice, these curves aren't so smooth. Okay? They're still continuous, they're still differentiable, okay? But these curves are only one-time differentiable. You can differentiate these curves once, but they don't have a second derivative. Yeah? The second derivative will be discontinuous everywhere. Okay? So these are only once differentiable functions. Okay? So this means they can change direction a lot faster. Yep, because the second derivative doesn't got to be smoothly varying. Change direction faster. People look at Matern 1/2, that has no derivatives. Matern 5/2, that has 2 derivatives. Okay? And by the time you get to 7/2, 3 derivatives, it essentially looks like an RBF kernel. You can't tell the difference by eye. Okay, there's a few kernels that we don't use that much in practice, unless you do kind of probability theory. This is a Brownian kernel. Okay, so this is the Brownian motion covariance function. Okay. So these curves are continuous almost everywhere, yep. But they are nowhere differentiable. Yep. So they have no derivatives. They're also infinitely variable. So what that means is, if I pick one of these curves and pick any segment from it, no matter how small, if I zoomed in enough, you could find the complete works of Shakespeare written in your own handwriting. Okay? Unbounded variation. Yep. So variable, if you zoom in, you'll find anything you want, in theory. Okay? Very variable. So they're the basis of stochastic calculus, of course. Another kernel, which you can kind of informally think of as the derivative of Brownian kernel, is white noise. Okay? So this kernel is 1 if x equals x prime. So the variance between f of x and f of x prime is 1 if we're at the same point. Okay? So the variance at that point is 1. Otherwise, the covariance is 0. So that means all points are uncorrelated. Yeah? So in other words, this is a nowhere continuous process. It's a white noise. every point is independent of every point, so it's not continuous anywhere. It's white noise. Yeah. Okay, one final example then is this is what's called the linear kernel. So here I've got k of x, x prime, is just equal to x times x prime. And what you can see here is this is lines, all start at 0, and then they're just straight lines forevermore. The question is, what's happening here? Why does that happen? Well, we can kind of generate this kernel. So let's think about a function y of x that is some constant c times x, where we don't know what c is. Give it a random distribution where it's normal, mean 0, variance 1. Yep. So this is our model, y of x. Let's work out what the covariance function is for y. Okay, so if we think about the covariance between y at x and y at x prime, that's the covariance between cx and cx prime. Only c's random here, x is fixed. So that is x times the covariance, or the variance of x, covariance of c with the covariance of c with itself, the variance of c, times x prime. Yeah? And we know the variance of c is 1. Yeah? So the kernel function, the covariance function for this is just x times x prime. Okay? And these curves are this, of course. This is straight lines through the origin. So that's how we get this here. Okay? So y of this form, our model here, this model y, is a Gaussian process, because it's Gaussian. It has 0 mean everywhere, and our covariance function, k, is given by this linear kernel. Okay? So this linear kernel gives particularly uninteresting, if you like, curves, just straight lines through the origin. Okay. Any questions at this point? Yeah, please. Yeah. Okay, so it's just, I've got two inputs here. So to say the covariance between 2 points, so we specify the Gaussian process for its mean and its covariance. Okay, so we need to be able to say, we pick out 2 indexes, and I've just called them x and x prime. I could call them x1 and x2. That makes sense? So have you got a pen, Richie? Yeah. So we've got our index set here, okay? And we've got our unknown function. And so we've got a value at x1 and x2. And so what I need to be able to say, if this is f of x, I need to say what the covariance is between f of x1 and f of x2. That makes sense? I've called it x and x prime. My thought. Yeah, they just go through the variable index. It doesn't need to be one of when it was a finite set, I had integers, didn't I? Index 1, index 2. But for functions, I could have it at 1.1 and pi. You know, just two values along here. I could do 0 and 5, yeah. Yep. So, you know, the covariance, if I let k x prime be my squared exponential, okay, I had 2, didn't I? I can put whatever I like in here. So the covariance between 0 and 5 is just e to the minus 25 over 2. Yeah?
I meant like the index between 0 and index and 5, not the value itself.
So these are the indexes here.
Oh, right.
Yeah, so this is the covariance between f at 0 and f at 5. Does that make sense?
Yeah.
Okay. Good question. Yes, please. It is an important modelling choice. It is, in practical applications. It's not if you have lots of data. Okay, so if you have lots of data, your covariance will swamp it. If your data is is plentiful compared to the dimension of your problem and the size of your input set, then it probably doesn't matter too much. But in practical applications where you don't have a lot of data, the mean function does matter. So what I meant by my poorly phrased comment was that it doesn't create many headaches for us. Okay? We can pick what we like there, and it matters. But in terms of the theory of Gaussian processes, it doesn't matter too much. The covariance function is what matters in terms of the theory. Okay. Good. Yeah, please. Say it again.
I added the realizations of white noise process are measurable in the covariance process.
You need to ask a proper mathematician. I'm sorry. I don't think I used to be a proper mathematician, but I don't think I ever knew the answer to that. So I don't know. Okay, sorry. Say the first bit of your question again. Yeah, they could be. So if your input was time, that could be the process at time 0 and at time 5. Yeah. So your process, you could be modelling temperature through time. So it could be day 0 or hour 0 and hour 5. I mean, the labelling matters in the sense that how it translates to the covariance function, but that's the only sense in which it matters. Okay.
When you talk about this function, so which function are we discussing about? Is it mainly the kernel or how X maps?
So the function we're modelling by our Gaussian process is the mapping from X to Y. The kernel function, the covariance function, is part of our specification for how that function varies with X. Okay? So K is something we choose. We choose K. We model F.
So here we are only discussing the linear case.
We're only discussing one-dimensional functions yet. Yep.
And also here each line is kind of a function of a sample.
Each line is a sample or a function. So a sample is a function. Yeah, so one sample is one function. The feedback is terrible on this. No. It's better, is it? Okay. Does that answer your question? Yeah, good question. What I'll suggest is let's talk in the break, okay? Because I think that's a detailed question, and we'll pick that up, okay? Yeah, please. Well, it really depends on the example. So, most processors aren't isotropic, and we don't often use isotropic kernels, but we nearly always use stationary kernels, and most processors aren't stationary. But it takes an awful lot of data to learn non-stationarity, so assuming stationarity is a good simplifying assumption that allows us to make progress. That is approximately true, hopefully, sometimes. And it's up to a particular situation for us to assess how true. Yeah? Yeah, please. Here, I do. It's x times x prime. Supposed to repeat it. We're supposed to, sorry, say that again. Well, we did essentially. So I made an assumption about what y is, okay? And I showed that the covariance of that kind of model is x times x prime. The converse, is that what you're worrying about, the converse? Whether, yeah, you need a stronger argument to show the converse that if the covariance is that, the lines are always that. It is, but I can't reconstruct that at this point. Okay? Yeah, good question. Last one, then we'll carry on. Yep.
Why would you take the Brownian motion as a covariance function when we make assumptions that it's stationary?
The Brownian motion was the only non-stationary kernel. Yeah, so this one's not stationary, all the others were stationary. Yeah. So is that what you're asking? Yeah, so that one is non-stationary, thank you. Yeah. Go on, last one. Yeah, go for it.
Could you just explain the difference between stationary and non-stationary?
Yeah, of course. So stationary means that if I translate my curve in the x direction, it'll look statistically the same. I believe, the curve between 1 and 2 looks the same statistically, has the same distribution as the curve between 10 and 11. Okay, I can translate it. That's what that means. Okay, let's carry on. There'll be plenty more time for questions. So, the properties of the GP are, as I mentioned, are primarily inherited from the covariance function, K. And so in particular, if the covariance function is continuous, and for stationary kernels, if it's continuous at 0, then the sample paths will be continuous everywhere. Okay? So what I'm trying to say, I guess, is it's very hard to tell from these kernels what the sample paths are going to look like. Yeah? Even after you've been doing this for a long time, I still have no intuition how we get from curves like this, covariance functions like this, to these curves. It's completely opaque to me. Yeah? And I think it is to everyone, really. There are some rules, we know, and these are the rules. It says the sample paths are continuous if the covariance function is continuous at 0. And similarly, the sample paths are differentiable if the kernel is differentiable. Are essentially the rules. So if the kernel function is twice differentiable, your sample paths will be twice differentiable. Now we have to be very careful when talking about differentiability and continuity of stochastic processes. It's a technical topic, but that's basically the rule of thumb here. The key thing is the way we operate covariance functions is we tend to pick a family, so exponentiated quadratic, say, on a turn, and then we let it have some free parameters, so these hyperparameters I talked about. So the length scale, the variance, and various other things. Okay? And then we try and estimate those from the data. Okay? So we pick a kernel that determines how differentiable it is, whether it's continuous, but how fast it varies and how widely it varies, we try and estimate by picking these hyperparameters, like the length scale and so on. Okay. So that just says that. And you can be as clever or as dumb as you like here most of the time. Okay? And it's helpful to do a bit of both. So, with the kernels, you can do Bayes factors or look at maximized marginal log likelihood. You can do predictive tests. So you can have a test data set and a training data set, fit to your training data set and predict your test data set and try different kernels to see what predicts best. You can do all these different things. Okay? And the hyperparameters, similarly, you can do it by maximum likelihood. That's the most common choice. Yeah, so it's just an optimization. But you can do full Bayesian inference here if you want. Do MCMC, whatever, to learn these things, to learn the distribution of them. Sometimes we need to cheat a little bit and help restrict the range of these hyperparameters. I'll show examples, maybe at the end, where we can get stuck in local minima, so it helps sometimes to help guide these things. And it's not really cheating, we're just trying to find something that predicts well. But we're not interested directly in these hyperparameters, we're interested in finding good models of our functions. Okay. So that's fine. So far, all very abstract. I've shown you some random curves, nothing to do with data or predicting. So why would we use these to model data? Well, it's because of these nice properties we talked about at the start. Okay. So first one is that if we add up Gaussians, they're still Gaussian. Okay. If you subtract Gaussians, they're still Gaussian. If you multiply by stuff, they're still Gaussian. Okay. So that's a nice property. Perhaps more importantly, for our point of view, is that they are closed under conditioning, Bayesian conditioning. Okay. So in other words, conditional distributions are still Gaussian. So in 2 dimensions, well, these could both be vectors, actually. Suppose we've got, well, I've written it in 2. So let's suppose this is a bivariate distribution. So we've got y, it's just 2 numbers with a mean vector and a covariance matrix. Now, we could work out, and we will work out, what the distribution is of y2 if someone came along and told you y1. Yep, so someone came and gave you the piece of information that y1 is this value, is 5 or whatever. Okay. There's a simple formula for saying what y2 is, what the distribution of y2 is. Okay. It's still Gaussian. We just update the mean, and we update the variance. That's all that's happened here. And this update, it's not very nice to look at, but it's simple. It's just linear algebra. It's matrix multiplication is all that is. And the same property carries over to Gaussian processes. To condition them on data is just going to be a case of linear algebra, something like this. Okay? And that is the reason why Gaussian processes are widely used, because of this simple fact. So I know we've been going quite slowly, that's fine. I think it's still useful just to outline why this is true a little. So let's think about the distribution of y2 given y1. Okay. So we can work out by the laws of conditional probability. This is just the joint distribution divided by the distribution of y1, which is just, we only care about the y2s here. So I can forget everything in y1 only. So that's just proportional to the joint density. So let's just write this out. Okay. So this first line is my Gaussian, multivariate Gaussian PDF. And all I've done here is then put in the mean vector and the covariance matrix. I've rewritten the covariance matrix. It's the inverse covariance matrix, so I've called the inverse Q here. Okay? And I haven't written the second term in, but this dot, dot, dot here is the same as this term here. Okay? It's that the difference between y and its mean divided by its variance squared, essentially. Okay? And what we're going to think is, what does this look like in terms of y2 only? So if I just collect the terms that have y2 in, I get a squared term, y2 minus its mean, times 1 over its variance, inverse of its variance, squared. So it's the deviation squared divided by its variance, plus a cross term, a y2 and a y1 term. Okay? Plus a load of other stuff. Yeah? But the other stuff only has y1 in, so I've dropped it. So I've got this proportional sign here. I only care about y2, if you've seen these kind of calculations before. So what is this? Well, this is e to something y2 squared plus something y2. Yeah? So a quadratic. So that is just a Gaussian PDF, right? That's what a Gaussian is. E to the quadratic. Yeah? So in other words, we've got here that the conditional distribution is still Gaussian. Now, to get the formulas we had on the previous slide, you just have to go and collect terms, basically. So there's a bit of tedious algebra. You just go collect up these terms. You can look in the slides afterwards. But we can just read off, essentially, what the updated mean and updated variance are. Okay. But just to show you that it's just a very simple thing underlying all this. Okay. So how does this translate to Gaussian processes? Well, remember what we said for Gaussian processes. If we have a finite number of them, finite number of points from our process, so let's suppose we're interested in the Gaussian process x1, x2, up to xn, and x, then we know that that has a multivariate Gaussian distribution, n plus 1 dimensions, with some mean vector mu, some covariance matrix sigma. Okay. And let's suppose we observe the value of f at x1 up to xn. Yeah, so someone comes along and tells you what f is at x1, f is at x2, so on. So this could be, back to our temperature example, through time. Maybe you know temperature on day 1, day 2, up to day n. Okay? And you want to know what's the temperature tomorrow. Yep? That's our x. X is tomorrow. Yep? So how do we get this distribution? Well, because this is a multivariate Gaussian, and we're just conditioning on some of its values, what we get here is that this is still Gaussian. Okay? But we've just got a new mean and a new variance. That's all that's changed. Okay? So if we think about this in pictures before we do it in maths, we started off with our prior distribution. These are our samples that we had before. So these are before we've seen any data, just random samples. Someone's then come along and told me the value of f here at 2, at 4, at 6, at 8, and at 10, those points here. Okay? So you can see at those points, I've only kept the curves that go for those points. Yeah? I want to know what's the distribution of the curves now that we know that they have to go through those data points, the values at 2, 4, 6, 8, and 10. Okay? And essentially, this is the algebra behind that. It gives us then a prediction of the function everywhere else. Okay? So this is the uncertainty that remains about our function. You can see that where the data points are, there's no uncertainty. It collapses. Okay? And in between the data points, we've got the best guess, which is the mean in blue, and the uncertainty, which is the grey bit around it. Okay? And that's the kind of picture you always see presented. So how do we get these values? Well, let's just skip ahead to that. How do we get those values? Well, we use exactly what we did before. Okay? So here we've got the situation where we've got n input, so we've got f at x1 up to xn plus the value at x, and we know that as a multivariate Gaussian distribution, and I've assumed here it means 0. Yeah? The covariance matrix is given by the kernel function. So the covariance between, the variance of f1 is kx1, x1. The covariance between fx1 and fx2 is kx1, x2, and so on. Okay? That's this matrix here. Okay? And I've kind of split it into parts. So the red part here is all the covariances between the fx1 up to fxn. Okay? The bit I'm going to assume we're going to see. The blue bit is the covariances between x1 and x, where x here stands for any other value. Okay. And then at the bottom corner, we've got the covariance between x and x. Okay, so the shorthand notation we often use is something like this. So this red bit here, I'm going to call capital K of xx. We call this often the gram matrix. This is the covariance matrix for the observed data. If we observe x1, f of x1, f of x2, xn. This is the correlation between what we want to predict and what we observed. This is the prediction bit. So I've just partitioned this matrix. This matrix just comes from our kernel. Okay. Then just directly writing down what we had before, exactly the same as we had with two variables, but now we've got n plus 1 variables. Okay. The distribution of f of x given the value of f at x1 up to f of xn is normal with a new mean function, I call it m bar of x here, and a new covariance function k bar of x. And the mean function is just this. It's just two parts of those matrix, the red part and the blue part. So we've got the blue part times the inverse of the red part times the observations, the f x1. Okay. So I know the first time, if you're seeing this for the first time, it looks all a bit confusing, but it is just populating a matrix with your kernel function and then doing a simple bit of linear algebra, a matrix inverse times two vectors, basically. Okay? And that tells us our updated mean and variance. And similarly, we get a new covariance function, which is the same parts as before, just compiled slightly differently. Okay? We know how to do linear algebra really well. Yep. So this largely is why Gaussian processes are popular. Okay? To fit them to data is, in some sense, trivial. It just requires linear algebra. Yep? And we've perfectly worked out the conditional distribution of our model given our observations. There are very few, if any, other processes for which that's true. That it's such a simple process to condition them on data. It normally takes a lot of effort to do these things. So that's why Gaussian processes are used everywhere. Okay. So some pictures then. So there's one kind of variation of this that I just want to explain, and that's around whether your model interpolates the data or not. So interpolation is where you go exactly through the data points. Okay? So here I've got a model that interpolates. So I've got 4 data points. I've observed the function at those 4 data points where those crosses are. Okay? And then what I've plotted is my mean function, the solid curve, and plus or minus 1.96 standard deviations around it. Okay, so I've got a 95% credible interval around the unknown function here. Okay? So just using directly what we had before. Nothing different, just what we've got here. But often we don't want to interpolate. We don't want to, if your data is noisy, you don't want to trust it completely. Perhaps you observe the value of the function with error. Perhaps if you're measuring temperature through time, your thermometer is a bit noisy. Got a tolerance of 0.1 degrees, something like that. So you don't want to interpolate perfectly. So often we don't observe f directly. We observe y, which is f plus an error term. Okay, so a small error. Or a big error, whatever. Okay. So the only way that changes anything is then we think about, well, what's the joint distribution of y1, y2 up to yn, and f of x? And all that's changed here is I've got a plus sigma squared times the identity matrix in here. That's all that's changed. Sigma squared times the identity, where the right shape to make that add. I've added sigma squared to each diagonal element in kxx. Then the updates, all I've done is, instead of where it's kxx before, I've got kxx plus my measurement error sigma squared times the identity. Okay, so nothing's changed apart from that one little bit. So what does that mean in pictures? Well, it means that we no longer interpolate the data perfectly. So here I've got a standard deviation of 0.1 in statistics, in Kriging. We often call this a nugget term. Machine learning, they call it an observation likelihood term. Okay. But I've got an error on the data of 0.1 here. So now we've got a mean function still that goes near the data. It doesn't exactly go through the points anymore. Okay. Although it's pretty close still, isn't it? But the uncertainty doesn't collapse at the data points. Yeah. We're not entirely certain of what the value of f is, even where the data are. Yeah? We'd need more data to tie it down better, because we've observed with error. If we make that nugget smaller, we get closer to interpolation. We get smaller amount of error around the data points, and so on. So this nugget term, this variance term, becomes another parameter in our statistical model that we need to estimate. When you're fitting a process, we're going to estimate these nugget terms. Okay. And just to say, for the mean function, there's lots of variations on this. So, if you have a linear mean function here, we can do lots of conjugate analyses, which I'm not going to get into. But, you can integrate out some of these parameters. But some of the parameters we are stuck with. So, the nugget parameter, the length scale parameter, we have to estimate that via some other procedure, like maximum likelihood or something like that. Okay. So, any questions at this point? Please.
Can you go back to the stereo function?
Will that one do?
Yeah, this is good.
Yeah.
So if I look at the
Yep.
Just the mean function will be different.
Yeah, very good point. I've got a slide on it later, which I probably won't get to, but one of the big failings of Gaussian processes, in some sense, is that this posterior covariance, y doesn't appear in this bottom line here. The data doesn't appear in that variance. So it doesn't matter what data we saw, that was always going to be our posterior variance. That's not quite true, because normally we'll have hyperparameters in the kernel. Okay? So there'll be 3 parameters in K, like the length, scale, and variance, and we'll estimate them, and we do learn them from the data. So the data does affect the posterior covariance function in that sense, but if you knew your kernel function exactly, then you're right, it doesn't appear, which feels like a weakness of Gaussian processes. Absolutely, good point. Any other questions? Yeah, please.
So we always assumed that the covariance matrix was invertible, but it could be possible due to the choice of the kernel that you cannot invert it.
Yep.
So I think this approach with the noise would be one way to solve this, but is there any other way to circumvent it?
Yes, it's a very good point, and it's a point you'll run into this afternoon probably in the lab sessions, is this gram matrix here isn't always invertible. Okay? For a whole variety of reasons, it quickly becomes ill-conditioned, which means non-invertible, essentially. Okay? Particularly if you've got very smoothly varying functions, so you've got an RBF kernel. We fix that instantly if we use a nugget term. Okay? So if you've got a term here plus sigma squared I, then in theory, any sigma squared bigger than 0 makes this invertible. Oh, there's an error there, sorry. This is the correct one. Yeah, the inverse is on the outside of the brackets. But in practice, we just increase sigma squared enough until this becomes invertible. I'm sure there are other ways. So you could do like a basis decomposition and take the leading modes, but nearly all software does that. Okay, and it doesn't tell you it's doing that either quite often. It just does it behind the scenes, and it'll just add a small amount of jitter to make it invertible. Any other questions? Okay, so just to briefly then talk about why we might like GPs. I'm going to skip that because it's quite technical. No, I'm not. Okay. So, one reason GPs are popular is we can think of them as a non-parametric extension to linear regression. Okay. So, the kernel we pick determines the space of functions we essentially are thinking about here. So let's think about linear regression for a minute. So linear regression says, given data y, x and y pairs, can we find the parameter beta that fits the best linear model, to predict y? So you might do that by minimizing the sum of squares plus a regularization term. Yeah? So this is a standard way to do linear regression, right? This is Lasso. Not Lasso, sorry, ridge regression. Yeah? Fitting beta here. Okay. Well, you all learned at university, if not at school, that, university type of ridge regression, I guess, the answer, the least squares estimator here, is just this formula here. Yeah? So x transpose x inverse x transpose y. Okay? If you've got ridge regression, you've got an extra term in it. Now we can rewrite this into what's called the dual form. So I won't talk about why or how, but it's in the slides if you want to look. So just a simple algebraic rearrangement of that can rewrite this in a different way. And just one thing I want you to note here, instead of having x transposed x, we've got x transposed in here. Okay? So at first, when we look at these two answers, these two ways of computing the same thing, the dual form looks harder than the normal form. So if x, our design matrix X, is an n by p matrix, where n is the number of data points, p is the number of features. Okay. The top row, the dual form, requires us to invert an n by n matrix, or n's the number of data points. The bottom one requires us to invert a p by p matrix. And in linear regression, of course, we normally have more data points than features. Yep, more data points than parameters, normally. Okay. But the key kind of observation here is that this dual form, because it uses x transposed, it only uses inner products between the input locations. So I'm assuming these are vectors here. Okay. So this you could write in terms of covariance functions as a gram matrix, our k from before, if we had this covariance function, k, which was x transposed x. Okay? And then if we go through and work out what the prediction is at a new location, so a new location x, in this dual form, what we get is exactly the Gaussian process update we had before. So this is the same formula we had earlier. Okay? So linear regression is just doing Gaussian process regression when we have this mean function, this kernel function, sorry. Okay. And every element here is this inner product, x transposed x prime. Okay. As I said, so this is exactly what we got before, the exactly same form. So this is where we can generalize from linear regression to something non-parametric. So the first generalization we might take is to have more features. So in linear regression, we can replace x by other things. You could have a 1 there to get a mean, an x squared, a sine x, or whatever. You could put x cubed, interaction terms. Yeah? You could get fancy as you like. And so what we could do is change this inner product from x transposed x to an inner product between features. Okay, so if these are my features, I now just do exactly the same as before, but using k in this form. Okay. And the clever thing is, the clever trick we rely upon is that for some sets of features, for some choices of this feature vector phi, we can avoid explicitly computing all these different things. Okay? So let's suppose I had this feature vector phi here that had all these terms in. Okay, so an x1, x1, x2, and x1 squared, and x1, x2, and x2 squared. Okay. So to do linear regression, to work out the kernel matrix here, with a bit of fiddling around, it turns out you don't actually need to do the inner product between these two sets of features. You don't need to do this line here. All you need to do is this simpler line here and square it. Okay, so there's a simple formula for computing the inner product between these two sets of features. Okay. So here, again, we've got 1, 2, 3, 4, 5, 6 features, so not many. We've got 6 different features. And the key thing is, to compute k, we didn't need to explicitly compute the feature vector. Yep, all I had to do was this thing here. I didn't need to compute what x1 squared was, or what x1, x2 was. Yes, go on. Ooh. Oh, it's just another x, I'm sorry. My x prime from before. Okay, sorry, yeah. Just a different label for the other input. Yeah, thank you. So this same idea, and I know I've gone too fast for the details here, but you'll see this again later in the week. Okay? The same idea works if we have an infinite number of features. This is what's called the kernel trick. Okay? So with certain sets of features, we can write down an infinite number of terms, and it turns out that all we have to do is compute the covariance function. Okay? And in fact, there's a theorem, Mercer's theorem, that says any valid covariance function can be written as a set of features, probably infinite dimensional set of features. So what we're doing when we pick k, even though we don't realize it at the time, is we are picking this feature vector phi. We're picking what we think our functions look like in some sense. Okay? We don't think about it very often in those terms, but it can be useful to think about it sometimes like that. Yeah? Whenever we pick k, we are picking the features phi. let's just see. Well, the reason that matters is that GP regression can be thought of as linear regression with this set of features. Okay. So just one example to see where the Gaussian exponentiated quadratic comes from. Suppose our features are all Gaussian bumps. So this would be like radial basis function regression. Okay? So for each x, we work out this bump, which is a Gaussian bump around C0, a bump around C1, around C2, and so on. So it's just a bunch of different features around each location. Okay? So that's all we've got here. And then we can show that if you think about the inner product of these features, this tends to, as you get infinite number of features, the RBF kernel. So when we do Gaussian process regression with the RBF kernel, it's kind of like doing this radial basis function regression, okay, which you might have seen in textbooks. It's not used very often anymore, but it was a common technique at some point. Okay. Okay, and there's lots to be said on all these things. This is the idea here of this kernel trick. What we've done, we've lifted our data to some infinite dimensional space in the hope that it looks simpler somehow there. Okay, so there are all these different kind of ways of thinking about Gaussian processes, and this is kind of one of the reasons people like them. It's a form of non-parametric regression. Okay, so I'll skip these other kind of bits. I've got lots of different justifications for why Gaussian processes have become so popular. And you can look through them if you want to. So just to conclude and talk briefly about the difficulties of using GPs, because you'll see this afternoon. Okay. There are often some problems. We know the theory works great for Gaussian processes if we know the right covariance function or the right hypothesis space, or whatever you want to think about. If you know those bits, it's beautiful. Okay? The problem comes in having to pick a good covariance function. So, as I said already, often we pick the covariance function from a small set and see if it works. So we might have a test data set and a training data set to see whether it predicts well. Yep. And if it doesn't, we know we need to go back and pick our covariance function. We know that we've said that the covariance function often contains hyperparameters, so I've got a variance here and a length scale, and we need to pick them somehow. So normally via maximum likelihood in an optimization. Okay? And so all the software will do this for you, you'll see this afternoon, but it goes wrong a lot of the time. And it can go wrong for a lot of reasons. The surface can be very flat. Okay? It can be multimodal. Okay? It might be that you need to help guide it to bits of parameter space, hyperparameter space that you like. An example that you might see is something like this. Okay? So here I've got 10 data points from a sine curve. Okay? And I fit a Gaussian process to it using the default settings in GPy, the software you'll look at later. Okay. And about 1 time in 10, you get an answer that looks like this. Okay. The answer we want it to look like, presumably, is like this. We know it's a sine curve. Okay. So we want something that goes through the data, wiggles around like a sine curve should. It's not quite a sine, is it? A sine plus a linear bit, I think. But 1 time in 10, the optimizer will find this value, which says, oh, this looks like a zero mean with no information at all. Everything's uncorrelated. It's just white noise with variation around the curve, okay, around a flat mean. Okay. And so we have tricks to try and get around these. We restart the optimizer, okay, 10 times, say, hoping it gets lucky and gets a good value. Okay. We try and rule out large values of the length scale. What's happened here is it says the length scale is very large, i.e. the curve's flat. Okay. I've got a big nugget, so I might limit the nugget to be small. So we'll talk about some of those tricks in the lab sessions this afternoon. But this is the main headache with using GPs, this problem of trying to find the hyperparameters and so on. Okay, and the cost as well, but other people will talk about that. So just to conclude then, I guess just the take-home points are, well, you all know, you wouldn't be here, that GPs have now become very widely used in machine learning, statistics, and science, okay, across and engineering, across a wide range of things. And the popularity really stems from the fact that it's, in many ways, a very natural family, the most natural kind of family of stochastic process to use for functions. Okay. It's got some flaws. Also, it's mathematically tractable. We can fit these things without having to spend a month doing MCMC. Yeah? You can try this out in a minute, yep, which is nice. And they've had a wide range of success across a kind of whole range of application areas. Okay, so thank you very much. Are there any questions? I can take them over